In this discussion, we will learn the basic central processing unit scheduling concepts. We'll also perform some exercises on several CPU scheduling algorithms. We also consider the problem of selecting an algorithm for a particular system. CPU scheduling is the basis of multi-program operating systems. So by switching the CPU among processes, the operating system can make the computer more productive. In this context, it is kernel-level threads, not processes, that are in fact being scheduled by the operating system. However, the terms process scheduling and thread scheduling are often used interchangeably. In this chapter, we use process scheduling when discussing general scheduling concepts and thread scheduling to refer to thread-specific ideas. So we have here the subtopics for CPU scheduling. Our goal for this chapter: in a single processor system, only one process can run at a time. Others must wait until the CPU is free and can be rescheduled. The objective of multiprogramming is to have some processes running at all times. That is to maximize CPU utilization. The idea is simple. A process is executed until it must wait, typically for the completion of some input-output request. In a simple computer system, the CPU then just sits idle. All this waiting time is wasted, and no useful work is accomplished. With multiprogramming, we try to use this time productively. Several processes are kept in memory at one time. When one process has to wait, the operating system takes the CPU away from that process and gives the CPU to another process. This pattern continues. Every time one process has to wait, another process can take over the use of the CPU. Scheduling of this kind is a fundamental operating system function. Almost all computer resources are scheduled before use. The CPU is, of course, one of the primary computer resources. Thus, its scheduling is central to operating systems design. The success of CPU scheduling depends on an observed property of processes. Process execution consists of a cycle of CPU execution and input-output wait. Processes alternate between these two states. Process execution begins with a CPU burst, then followed by an input-output burst, which is followed by another CPU burst, then another input-output burst, and so on. Eventually, the final CPU burst ends with a system request to terminate its execution. The duration of CPU bursts have been measured extensively, although they vary greatly from process to process and from computer to computer. They tend to have a frequency curve. The curve is generally characterized as exponential or hyper-exponential, with a large number of short CPU bursts and small number of long CPU bursts. An input-output bound program typically has many short CPU bursts. A CPU-bound program might have a few long CPU bursts. This duration can be important in the selection of an appropriate CPU scheduling algorithm. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue. So the selection process is carried out by the short-term scheduler or CPU scheduler. The scheduler selects a process from the process in memory that are ready to execute and allocates the CPU to that process. The ready queue is not necessarily a first-in, first-out queue. When we consider the various scheduling algorithms, a ready queue can be implemented as first in, first out queue, a priority queue, a tree, or simply an ordered linked list. Conceptually, all the processes in the ready queue are lined up waiting for a chance to run on the CPU. So the records in the queues are generally processed on the process control block. CPU scheduling decisions may take place under the following four circumstances. Number one, when a process switches from the running state to the waiting state, for example, as the result of an input-output request or an invocation of wait for the termination of a child process. Number two, When a process switches from the running state to the ready state, like for example, when an interrupt occurs. And number three, when a process switches from the waiting state to the ready state, example, at the completion of input-output. Lastly, on number four, when process terminates. So for situations 1 and 4, there is no choice in terms of scheduling. A new process, if one process exists in the ready queue, has to be selected for execution. There is a choice, however, for situations 2 and 3. When scheduling takes place only under circumstances 1 and 4, we say that scheduling scheme is non-preemptive or cooperative. Otherwise, it is preemptive. Under non-preemptive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU either by terminating or by switching to waiting state. This scheduling method was used by Microsoft Windows 3. Windows 95 introduced preemptive scheduling, and all subsequent versions of Windows operating systems have used preemptive scheduling. The Mac OS X operating system for the Macintosh also uses preemptive scheduling. Previous versions of Macintosh operating system relied on cooperative scheduling. Cooperative scheduling is the only method that can be used on a certain hardware platforms because it does not require the special hardware. For example, a timer needed for preemptive scheduling. Another component involved in the central processing unit scheduling function is the dispatcher. The dispatcher is the module that gives control of the central processing unit to the process selected by the short-term scheduler. This function involves the following: switching context, switching to user mode, jumping to the proper location in the user program to restart that program. The dispatcher should be as fast as possible since it is invoked during every process switch. The time it takes for the dispatcher to stop one process and start another running is known as the dispatch latency. Different CPU scheduling algorithms have different properties, and the choice of a particular algorithm may favor one class of processes over another. In choosing which algorithm to use in a particular situation, we must consider the properties of the various algorithms. Many criteria have been suggested for comparing CPU scheduling algorithms, and which characteristics are used for the comparison that can make a substantial difference in which algorithm is judged to be best. The criteria include the following. Una, CPU utilization, because we want to keep the CPU utilization as busy or the CPU as busy as possible. Conceptually, CPU utilization can range from 0 to 100%. In a real system, it should range from 40% for a lightly loaded system up to 90% naman for a heavily loaded system. Next concept is throughput. If the CPU is busy executing processes, then work is being done. One measure of work is the number of processes that are completed per time unit. This is called throughput. For long processes, this rate may be 1 process per hour. For short transactions, it may be 10 processes per second. Next criteria is the turnaround time. From the point of view of a particular process, the important criterion is how long it takes to execute that process. The interval from the time of submission of a process to the time of completion is the turnaround time. Ulitin po natin. The interval from the time of submission of a process to the time of completion is the turnaround time. Turnaround time is the sum of the periods spent waiting to get into memory, waiting at the ready queue, executing on the CPU, and doing the input-output. Next criteria is the waiting time. The CPU scheduling algorithm does not affect the amount of time during which a process executes or does input-output. It affects only on the amount of time that the process spends waiting in the ready queue. Waiting time is the sum of the periods spent waiting in the ready queue. Next is the response time. In an interactive system, turnaround time may not be the best criterion. Often, a process can produce some output fairly and early and can continue computing new results while previous results are being output to the user. Thus, another measure is the time from the submission of a request until the first response is produced. This measure is called response time. It is the time it takes to start responding, not the time it takes to output the response. The turnaround time is generally limited by the speed of the output device. It is desirable to maximize CPU utilization and throughput and minimize turnaround time. Also, the waiting time and the response time. In most cases, we optimize the average measure. However, under some circumstances, we prefer to optimize the minimum or maximum values rather than the average. For example, to guarantee that all users get good service, we may want to minimize maximum response time. Investigators suggested that for an interactive system like your desktop systems, it is more important to minimize the variance in the response time than to minimize the average response time. A system with reasonable and predictable response time may be considered more desirable than a system that is faster on the average but is highly variable. Little work has been done on CPU scheduling algorithms that minimize this variance. As we discuss the various CPU scheduling algorithms, the following section, we illustrate their operation. So an accurate illustration should be involve many processes and each sequence of several hundred CPU bursts and input-output bursts. Now for simplicity, through we have to consider only the CPU burst in milliseconds. Ito po yung gagamitan natin time unit per process in our example. So the next would be the different CPU scheduling algorithm, and all the time will be described in terms of milliseconds. Our measure of comparison is the average waiting time. People, for reference purposes and informality, I would like to repeat again the discussion on the CPU scheduling algorithms, though it was previously discussed during our synchronous class, para isang buo po yung recording natin. So by far, the simplest CPU scheduling algorithm is the first come first serve. So with this scheme, the process that requests the CPU first is allocated the CPU first. The implementation of the first come first serve policy is easily managed dahil ito po ay naka first in first out queue. When a process enters the ready queue, its process control block is linked onto the tail, yung sa bandang dulo. So yung mga nasa unahan, it has to be on the front, and all other processes that comes after will be in the tail of the queue. So when the CPU is free, it is allocated to the process at the head of the queue. So again, meron po tayong front or head, and then yung bandang dulo ng queue is what we call the tail. So the running process is then removed from the queue. The code for the FCFS scheduling algorithm would be implemented using the first in, first out. So, subukan po natin itong example na to. Suppose that there are three processes. Yung order is we have P1 on the front. So, comes after, we have process P2, and yung pinaka-tail po natin is on process P3. Yung pinaka-dulo, kasi siya po yung pinaka-last na dumating. So, we have to represent this on a Gantt chart. Suppose ito yung pag-process ni CPU. So, to represent this, we have this Gantt chart for now. So, let us schedule this process. Now, on our example here, we say that we have process P1 at the front. So, then, isasalang po ni CPU scheduler si process P1. Process P1 has a burst time of 24 milliseconds. So, at time 0, since siya po yung nauna sa queue, si process P1 has to be served. Process P1 will not endure any waiting time. Bakit? Kasi po siya yung nauna. Bakante yung CPU, and then isasalang si process P1. So, our burst time is 24. That is, 0 plus 24 is equal to 24. At time 24, process P1 is finished. Comes after is process P2 with a burst time of 23. So we have here process P2. When you are to organize Gantt chart, please try to be consistent as well with the time interval. So si 24 ay mahaba kaysa sa 3, so then it has to be represented with this space here with the length. So process P2 has a burst time of 3. 24 plus 3 is equal to 27. Comes after process P2 is process P3 with a burst time of 3. So we have process P3 here. 27 plus 30 is equal to 30 milliseconds. Ibig sabihin, at 30 milliseconds, process P1, process P2, and process P3 are finished. Now, if we have to consider the waiting time, so we have to compute the waiting time for independent processes. So process P1, wala po siyang waiting time because the CPU is available. Then comes after process P2, the waiting time is 24. Comes last is process P3 and the waiting time is 27 dahil inantay po niya si process P2 matapos. So for you to compute for the average waiting time, sum up all the waiting time for these individual processes. That is 0 plus 24 plus 27. The result would be divided on the number of processes. So how many number of processes we have here? We have 3 processes. Divided by 3, this will result to 17 milliseconds. This is our time unit for this implementation or examples. Okay, let's have another example. So if the process arrived this time in the order of process P2, P3, and P1. So ito naman po yung ating head of the queue. Ito yung head at ito yung ating tail. So the order, this is the head. Okay, the order is P2, then P3, then P1 yung pinakadulo. The results will be now in the Gantt chart. So the average waiting time is 6 plus 0 plus 3. Ito, 6 plus 0 plus 3. So pag nagko-compute po tayo ng average waiting time, it doesn't necessarily mean that it has to be in order. Okay, importante yung ating sagot po ay tama. Now, if we are to analyze this, as this will be rooted from our Gantt chart, we say that in the order is process P2 first, process P2, yung previous example po natin kanina, yun din po yung ating reference for our burst time. Papakita ko po uli. Ayan. So, ito po yung ating burst time sa bawat processes. However, we are now particular with the order. So, process P2, in this example, comes first. So, it has a burst time of 3 milliseconds. That's why we consider 0 plus 3 here. Comes after process P3 with a burst time of 3 milliseconds. So, we have 3 plus 6. 3 plus 3 is equal to 6. And then, comes last is process P1. Si process P1, yung kanyang burst time is 24 milliseconds. That is, 6 plus 24 is equal to 30 milliseconds. Now, our waiting time then, process P1, tingnan po natin, ito si process P1, nagantay po siya ng 6 milliseconds. Then, comes after is process P2. Si process P2, nagantay po siya ng 0 milliseconds. Siya po na isa lang. And then, process P3 waited for 3 milliseconds. So, the average waiting time is computed according to the sum of the waiting time of these processes, these 3 processes. So, in this sequence now, we have 6 plus 0 plus 3 divided by 3, which is the number of processes. So, if this is the case, so the average waiting time is 3 milliseconds. This is much better than the previous case. So, there is the convoy effect. Anong ibig sabihin ng convoy effects? So, at this point, the CPU bound processes will then move back to the ready queue. So, we have the set of processes allocated according to the front and the tail. So there is a convoy effect as all the processes wait for the one big process to get off the CPU. So, ano po yung nauna? Yung mga maliliit na processes. And it is waiting for one big processes to get into the CPU. The convoy effect is phenomenon associated with the first come, first serve algorithm in which the whole operating system slows down due to few slow processes. This effect results in a lower CPU device utilization because it is coming with the shorter processes first, followed by the bigger processes. All the first come first serve scheduling algorithm is non-preemptive. So, yung unang example natin, non-preemptive din. Ibig sabihin, once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU. So, either by terminating or by requesting the input-output process. The first come first serve algorithm is quite troublesome when it comes to time sharing. It is important that each user get a share of the CPU at regular intervals. So it would be disastrous to follow one process to keep the CPU for an extended period. So in this case, meron po tayong starvation on process P1. A different approach to CPU scheduling is the shortest job first. Pangalawa na po to. This is the SJF scheduling algorithm. This algorithm associates with each process the length of the process of the next CPU burst. So when the CPU is available, it is assigned to the process that has the smallest next CPU burst. So if the next CPU burst of the two processes are the same, FCFS scheduling is used to break the tie. Note that more appropriate term for this scheduling method would be the shortest next CPU burst algorithm. Medyo mahaba because scheduling depends on the length of the next CPU burst of a process. So rather than its total length. We use the term SJF because most people and textbook use this term to refer to this type of scheduling. At saka madaling tandaan si SJF. Okay, let's have the example. So, we have here 1, 2, 3, 4 processes. Okay, so yung 4 processes natin has its corresponding burst time here. Now, if we are to organize this on our Gantt chart, we have to consider the shortest burst time. So, ito po yung ating reference. So, our consideration is that the length of the burst time. So, if we are to put an order, so, ang mauuna po is process P4. This is first with 3 milliseconds. Comes after is process P1. Ito po yung pangalawa nating isasalang. And then, we have process P3 on third. And lastly, we have process P2. So, as we organize this on our Gantt chart, we have to consider process P4 first. So, we have 0 plus 3. Comes after is process P1. So, we have 3 plus the burst time of process P1, which is 6. 6 is 9 milliseconds. Then, that comes after, itong pangatlo is process P3 with a burst time of 7. So, we have 9 plus 7 is equal to 16. Comes last is process P2 with a burst time of 8. So, 16 plus 8 is equal to 24 milliseconds. So, at 24 milliseconds, ibig sabihin, natapos po yung apat na processes na to. Now, to compute for the average waiting time, we say that we have to sum up the waiting time of the individual processes. So, we have 3 plus 16 plus 9 plus 0. These are all the waiting time of these 4 processes divided by, of course, 4. Bakit? Because these are the number of processes. And the result is 7 milliseconds. So, this is an SJF on an implementation of non-preemptive. Non-preemptive. Ibig sabihin, once the processes is loaded, by the CPU scheduler, it has to endure the burst time until it is done. So, until then, na may dumating na naman na input-output burst, and that is sasalang po siya uli. So, again, this is non-preemptive. Lahat ng processes has to endure, and that it has to be finished the moment it is loaded on the CPU. The SJF scheduling algorithm is optimal. So in that, it gives minimum average waiting time for a given set of processes. So moving a short process before a long process decreases the waiting time of the short process more than it increases the waiting time of the long process. Consequently, the average waiting time decreases. So kung ikukumpara natin yung dalawang example kanina, the waiting time for the SJF is shorter compared to the first come first serve example. The real difficulty with the SJF algorithm is knowing the length of the next CPU request. The next CPU burst is predicted as an exponential average of the measured lengths of the previous CPU burst. So we can define exponential average with the formula here. Let Tn be the actual length of the CPU burst, and you have n plus 1 to be our predicted value for the next CPU burst. So then we have here the expression that defines n plus 1, which we have to compare the process. Alpha is our process, and checking on the previous processes from the processes that starts at 0 time, and processes comparing this on the next coming processes. So the value of the Tn constrains our most recent information, while the n here stores the past history. So the parameter controls the relative weight of the recent and past history in our prediction. The figure here shows an exponential average. The SJAF algorithm can be either preemptive or non-preemptive. The choice arises when a new process arrives at the ready queue while the previous process is still executing. The next CPU burst of the newly arrived process may be shorter than what is left of the currently executing process. A preemptive SJF algorithm will preempt the currently executing process, whereas a non-preemptive SJF algorithm will allow the currently running process to finish its CPU burst. Preemptive SJF scheduling is sometimes called the shortest remaining time first scheduling. So to support further the illustration here, let us proceed in this slide. So if our alpha is equal to 0, then n plus 1, and it implies that recent history has no effect. So meaning the current conditions are assumed to be transient. If alpha is equal to 0, then n plus 1. And the only most recent CPU burst matters, meaning history is assumed to be old and irrelevant. Now, to understand the behavior of the exponential average, we can expand the formula for n plus 1 by substituting for n plus 1. So in this case, we consider the predicted burst time of the previous process and the burst time of the process that actually occurred. So typically, if it is less than 1, as a result, 1 minus is also less than 1, and each successive term has less weight than its predecessor. So let us now execute or implement an example on SJF with preemption. Given this table, we have 4 processes on the queue. So this is the order of the processes. However, this time, we have the column for arrival time, and of course, the corresponding burst time for every processes. Now, as we consider the arrival time, we say that process P1 arrived first. So among these 4 processes, process P1 arrived first. So then process P1 is scheduled for processing. Now the burst time of process P1 is equal to 8 milliseconds. So this process P1 has to be endured for 8 milliseconds. Only that during the processing of process P1 at time 1, process P2 arrive. So if we are to consider the burst time of these two processes, process P2 is shorter compared to process P1. So then process P1 has to be preempted to give way for the shorter process. So process P2 is now on process. Process P2 has a burst time of 4 milliseconds. Okay, only that while processing process P2 at time 2, ito, at time 2, process P3 arrives. So, this is 2, 3, 4, and 5. So, at time 2, dito po dumating si process P3 with a burst time of 9. So, if we are to compare the burst time of the current process, which is process P2, it is shorter to process P3. So, this new process this process P3 cannot preempt the ongoing process of process P2. And then, also, at time 3, dumating din si process P4. So, process P4 has a burst time of 5. Okay, 5. So, ang current process is process P2. Now, if we are to compare process P2 and process P4, mas shorter si process P2. So, this process P4 cannot preempt the process of process P2. Okay, so, ang mangyayari, pipila po sila sa queue. Okay, so, it has to finish first process P2, since process P2 is the shortest. So, 0 to 1, this is for process P1. P1 preempted by process P2. So then, since process P2 is the shortest among all other processes, it has to finish all the tasks associated for process P2, and that is 1 plus 4 is equal to 5. Okay? After process P2, i-evaluate po dito si burst time. So, among other processes, the next shortest burst time is process P4. So, process P4 has to be loaded by the CPU scheduler. So, the burst time for process P4 is 5. 5 plus 5 is equal to 10. So, process P4 is finished. Then, comes after is process P1. Bakit si process P1 po yung next? So, ang natitirang job is process P3. Ito yung natitira. At saka si process P1. Kaya lang, if we are to consider the shortest among these two, ito, 7 yung natitira because this was preempted. Meron na pong tapos na 1 millisecond dito. And then, ang next is process P3 na 9. So, in between this, 7 and 9, the shortest is 7. So, what we do, we have to load process P1 and then add its burst time. So, 10 plus 7 is equal to 17. 17, and then the burst time for process P3, which is equal to 9. 17 plus 9 is equal to 26. Okay, so if we are to compute for the average waiting time, we have 10 minus 1 plus 1 minus 1, 17 minus 2, and then 5 minus 3 divided by 4. So, it is 26 divided by 4 is equal to 26 divided by 4 is equal to 6.5 milliseconds. Okay, so this is the average waiting time for the SJF here. Now, if you are to compare non-preemptive SJF scheduling, it would result to 7.75 milliseconds. So, in this case, our SJF with preemption has the least average waiting time comparing to the other SJF with non-preemption, even when we are to compare this with FCFS, still SJF with preemption has the least average waiting time. Okay, this is now the third CPU scheduling algorithm. The first one was FCFS, then we have the SJF. Next is the priority scheduling. Now, a major problem with priority scheduling algorithm is indefinite blocking. Check po natin yan, si indefinite blocking, or sometimes we call this as starvation. A process that is ready to run but waiting for the CPU can be considered blocked. So, a priority scheduling algorithm can leave some low priority processes waiting indefinitely. A solution to the problem of indefinite blockage of low priority processes is aging. Aging involves gradually increasing the priority of processes that wait in the system for a long time. So, if I have, for example, 5 processes at si P5 yung pinakadulo. Every time na ma-accomplish po yung isang process that comes ahead of P5, nababawasan po kanya yung kanyang waiting time. So as it age, yan po ay nagkakaroon po siya ng chance to be executed on the CPU. So let's try to check the example of this processes here. Suppose there are 5 processes, namely process P1, P2, P3, P4, and P5. So we have the burst time, then we have the priority. Notice that this is the new column now. We have the priority. Now, with the priority given here, we say that we have the integer. So, if, say, the CPU is allocated, ito po yung given, the CPU is allocated to the process with highest priority, where the smallest integer has the highest priority. So, ibig sabihin, we have to proceed in ascending order. So, 1, then 2, then 3, 4, and 5. So, our first priority here is process P2. Okay, so process P2 has to be endured first. It has to be allocated to the CPU, and that it has a burst time of 1. So, 0 plus 1 is equal to 1. Comes after process P2. Second in the queue is process P5, and it has a burst time of 5. So, 1 plus 5 is equal to 6. Comes after is this third priority, which is for process P1. Process P1 has a burst time of 10. So, 6 plus 10 is equal to 16. Then, comes next is process P3, priority number 4, and the burst time is equal to 2. So, process P3, 16 plus 2 is equal to 18. And the last priority is process P5 with a burst time of 1. Okay. And that last priority is process P4. Okay, process P4. And then, ang burst time niya is 1. So, then, we have 18 plus 1 is equal to 19. At 19 milliseconds, all processes are finished. This is the implementation using priority scheduling. Our next implementation is priority scheduling, this time with preemption. So we have the information on the given table. We have the process ID, the arrival time, burst time, and priority. So we have process P1 to be considered first because it arrived at time 0. So it has to be plotted, it has to be loaded by the CPU scheduler. So then process P1 has to be accommodated first. So while process P1 is being processed, at time 2, process P4 arrived. So process P4 has a priority of 1. If we are to compare this with process P1, P4 has the priority compared to the previous process. So, process P1 has to be preempted. And since there is now the processes executed for process P1, this set of processes has to be deducted from the total burst time of P1. So, 11 minus 2 is equal to 9. We still have 9 milliseconds for process P1. So, this has to be on a queue for now. Since process P4 was loaded, then process P4 has to be endured. So, however, if we are to check on the arrival time, at time 5, meron pong dumating na process which is process P2. Process P2 has a priority 0. Siya po yung pinaka-highest priority among others. So then, process P4 has to be preempted at time 5. So, may na-process naman po sa kay process P4, that is 3 milliseconds. This has to be deducted on the total burst time for process P4. 10 minus 3 is equal to 7. We still have 7 milliseconds for process P4. So, since it was preempted, then it has to be on a queue. What comes next is process P2 with the highest priority. Process P2 has a burst time of 28 milliseconds. So, this has to be endured first. This has to be accomplished first since it has the highest priority. 5 plus 28 is equal to 33 milliseconds. At 33 milliseconds, process P2 is finished. So, lalagyan na po natin siya ng OK. Next, we have process P4. Siya po yung kasunod. So, priority 0, then priority 1. Priority 1 is for process P4 with a remaining burst time of 7. 33 plus 7 is equal to 40. So, at 40 milliseconds, si process P4 ay natapos. Lalagyan na po natin siya ng okay. So, we have 0, 1. Comes next is process P1. So, ang natitirang burst time kay process P1 is 9 milliseconds. 40 plus 9 milliseconds is 49 milliseconds. So, at 49 milliseconds, process P1 is finished. Lalagyan na po natin siya ng okay. So, comes next is the third priority, which is for process P3. Process P3 has a burst time of 2 milliseconds. So we have 49 plus 2 is equal to 51 milliseconds. So at 51 milliseconds, process P3 is finished. So ito matutuloy na yung okay ni P3. Next is the next priority. 3, then 4. So we have process P5 on the last priority. Process P5 has a burst time of 16. So 51 plus 16 is 67 milliseconds. At 67 milliseconds, process P5 is finished. Okay, so this time it is still a priority scheduling. However, we have preemption on its implementation here. So with preemption implementation, we have to check on the arrival time and the priority of the process. The round-robin scheduling algorithm is designed especially for time-sharing systems. It is similar to first-come, first-served scheduling, but preemption is added to enable the system to switch between processes. So a small unit of time called time quantum or time slice is defined. A time quantum is generally from 10 to 100 milliseconds in length. The ready queue is treated as a circular queue. The central processing unit scheduler goes around the ready queue, allocating the central processing unit to each process for a time interval of up to 1 time quantum. So to implement RR or round robin scheduling, we again treat the ready queue as first in, first out queue of processes. New processes are added to the tail of the ready queue. So the CPU scheduler picks the first process from the ready queue, sets a timer to interrupt after 1 time quantum, and dispatches the process. One of two things will then happen. The process may have a CPU burst of less than 1 time quantum. So in this case, the process itself will release the CPU voluntarily. The scheduler will then proceed to the next process in the ready queue. If the CPU burst of the currently running process is longer than 1 time quantum, the timer will go off and it will cause an interrupt to the operating system. So a context switch will be executed. The process will be put to the tail of the ready queue. So the CPU scheduler will then select the next process in the ready queue. Round-robin CPU scheduling algorithm is implemented in both preemption and non-preemption. So I'll have first the non-preemption implementation in this example. So if we use a time quantum of 4 milliseconds, all processes arrives at time 0. So given the time sabay-sabay po silang dumating, then we'll have the process P1, which gets the first 4 milliseconds, then followed by the next. So let's try to evaluate this. So we have process P1 has a burst time of 24 milliseconds. Given that we have our time quantum na equal to 4, ibig sabihin, we'll only get a time slice of 4 from this 24 milliseconds. So as we will load this in our Gantt chart, it will get the first 4. So 24 minus 4, there is still remaining 20 milliseconds for process P1. What comes next is process P2. Si process P2 has a burst time of 3. So, 3 lang yung kanyang hinihingi, but our time quantum is more than enough. So, yung binibigay po sa kanya na resource is 4 milliseconds. So, then, once this process P2 is loaded, it will immediately finish. So, lalagyan na po natin siya ng okay because this 3 milliseconds is to be loaded completely here. So, 4 plus 3 is equal to 7 milliseconds. Comes after is process P3. Process P3 has a burst time of 3. So, 7 plus 3 is equal to 10 milliseconds. At 10 milliseconds, process P3 is finished. Okay, so yung natitira na lang natin is process P1 with the remaining burst time of 20 milliseconds. Yun pa yung natitira sa kanya. But since we have only time slice of 4, we have to deduct 4 at a time. So 20 minus 4 is equal to 16. And we have to add it here. 10 plus 4 is equal to 14. So bawasan naman yung next cycle. We have 16 minus 4 is equal to 12. So, yeah, dadagdag po natin dito. 14 plus 4 is equal to 18. On the next cycle, we have to deduct the time slice again. 12 minus 4 is equal to 8. So, here, we have to add that time slice. 18 plus 4 is equal to 22. So, we have to continue on executing process P1. 8 minus 4 is equal to 4. So, we have to add it here. 22 plus 4 is equal to 26 milliseconds. So, still, we have remaining 4 milliseconds. It has to be loaded. 4 minus 4 is equal to 0. We have to add it here. 26 plus 4 is equal to 30 milliseconds. So, since we have no more task to be accomplished, natapos na po yung kay process P1, we have to terminate. So, at time 30 milliseconds, process P1 and the rest of these processes are now finished. Okay? So, this is for the implementation of round robin without preemption. Now, we have to consider some values here, like the turnaround and the waiting time. Although you're familiar with the waiting time, but let us try to implement this waiting time in the consideration of round robin. So first, we have the turnaround time. The formula for the turnaround time is completion time minus arrival time. So we have to we can also organize this in a column, like we have the process ID and then you have the completion time. Completion time is the consideration of these processes. Ito po siya ang completion time ng lahat ng processes. So, let's consider halimbawa si process P1 here. The completion time for process P1 is 30 milliseconds. Dito po siya natapos si process P1. Although, it was iterated several times, but finally, it was accomplished at 30 milliseconds. Now, as we evaluate for process P2, the completion time is at 7 milliseconds. It was loaded once and then it was completed immediately. So, at 7 milliseconds, process P2 is finished. Process P3, okay, ito po yung kanyang completion time and we have to note it here. So, since we have now our completion time, we can now work with our turnaround time. Turnaround time is completion minus arrival time. We have the given arrival time for all the processes here, which is equal to 0. So 30 minus 0 is equal to 30 milliseconds. 7 minus 0 is 7. 10 minus 0 is 10 milliseconds. So this is the turnaround time of the three processes. How about the waiting time? The waiting time has a formula. Ito siya, turnaround time minus burst time. So look at the table here. So if we are to consider process P1, our turnaround time for process P1 is 30 minus its burst time, which is equal to 24. So we have here for process P1, 30 minus 24 is equal to 6. Same as with process P2. titingnan po natin yung kanyang turnaround time at saka yung kanyang burst time. 7 minus 3 is equal to 4. Process P3, 10 minus 3 is equal to 7. So, ito po yung mga waiting time ng mga processes. Now, to arrive with average waiting time, you have to add all the waiting time of these processes divided by 3. Okay? So, in this case, meron din po tayong another method for waiting time. Now, in this method, maybe you are only referring to the Gantt chart. Ito lang po yung available sa inyo. Say we have the formula here. Waiting time is equal to the last start time. Ito, the last start time minus arrival time minus preemption times time quantum. Let's try this on process P1. So, say process P1, the last start time of process P1 is here. So, it's 26. This is the last start time. Minus 0. 0 is the arrival time. Minus 5. Bakit naging 5? 5 is the preemption. Now, let's try to check. Unang preemption ni process P1 happens here. Okay? So, na-preempt po siya because of the time slice. So, we have 1, 2, 3, 4, and 5. Okay? So, since we have 5 preemption for process P1, we have to note it here as well. Okay? So, we have 5 here times 4, which is the time slice or the time quantum. You might ask, bakit hindi po natin nabilang ito? Because this one did not endure. Okay? Hindi pa po siya nag-switch. At tinitingnan po natin is yung na-preempt. So, in this case, hindi po siya na-preempt. Tapos po dito yung process P1. Next, the consideration for process P2. So, process P2, we have the last start time. Check on the Gantt chart. Ito po siya. So, we have 4 minus the arrival time on the given. You have here, arrival time of all the processes is 0. So, 4 minus 0 minus its preemption. Hindi po na-preempt ever si process P2 because once it was loaded, agad-agad tinapos po siya because the time quantum is 4. Ang hinihingi po ni process P2 is only 3 milliseconds. Okay, so 4 minus 0 and then 0 times 4 is equal to 4. Same as with the concept of process P3, we have the last start time of process P3 which is 7 milliseconds. Ito, minus the arrival time, minus the preemption. Hindi po siya na-preempt because it was executed immediately. And then times 4. So, we have the average waiting time for each of these processes. The waiting time. Now, if you are to get the average waiting time, all you need to do is to add all the waiting time of these 3 processes divided by 3. Okay, this is an implementation of round robin in a method non-preemption. Okay, this time we have the implementation of round robin with a given arrival time. So let me just write here the clock. So we have to take note that on the arrival time 0, 1, 2, 3, and 4, there are associated processes. So process P1 arrive at time 0. This is for process P2. This is process P3, P4, and process P5. Okay, let's try to simulate now. On process P1, meron po tayong consideration ng 5 milliseconds. So, the time slice is only 2. So, we have to get only a cut of 2 milliseconds. 5 minus 2, we have 3 milliseconds remaining for process P1. So, we have to add it here. 0 plus 2 is equal to 2. Now, in between time 0 to 2, there are processes associated to this arrival time. So, first we have process P1 accommodated. And then, we have process P2. So, pumila po dito si process P2. And pumila din po dito si process P3. Okay? So, comes after process P1 is process P2. We have to load process P2 here. Now, since it is only limited to time quantum, we have 3 minus 2 is equal to 1. So, yung 2 dito mapupunta, 2 plus 2 is equal to 4. So we have now accommodated 2 milliseconds for process P2. Okay. Comes after is process P3. So si process P3 has a burst time of 1. So matatapos po kaagad si process P3 since you are given of time quantum which is equal to 2. 4 plus 1 is equal to 5. So si process P3 is finished at 5 milliseconds. Lalagyan na po natin ng okay. Next, tapos si process P3, na-accommodate na po siya. Then, we have process P1. So, si process P1, ang remaining time, burst time is 3. 3 minus 2, we still have 1 milliseconds after this. So, plot natin si process P1. 5 plus 2 is equal to 7 milliseconds. Okay? So, next, we will have process P4. So, after this, pagkatapos po ng 0 to 2, comes 2, 3, and 4. Ano po yung mga processes associated in this slot? So, we have here process P4, okay, at time 3, and then we have process P5 at time 4. So, ilalagay po natin yung processes. Okay, so next to be accommodated now is process P4. So, we will get time slice of 2. So, sakto na ang hinihingi niya is only 2. So, at this cycle, process P2 or process P4 I mean is finished. So, 7 plus 2 is equal to 9. Comes after, X na po natin si P4. Comes after is process P5. It has a burst time of 3. 3 minus 2 is equal to 1. So, may 1 na natitira po kay process P5. So, we have to add the 2 here. 9 plus 2 is equal to 11. X ko na po ito si process P5. Then, you have process P2. Ilan po yung natitira kay process P2? We still have 1 millisecond for process P2. So, 11 plus 1 is equal to 12. At 12 milliseconds, process P2 is finished. Okay? Next, ano pa po yung natitira? We still have processes for process P1 and process P5. So, process P5 is ahead of the queue. So, then, the process P1 is ahead of the queue with the remaining 1 millisecond. So, we have to add this 1 millisecond here. 12 plus 1 is equal to 13. At 13 milliseconds, process P1 is finished. So, lalagyan na po natin na okay. So, lastly, we have process P5. Process P5, yung natitira sa kanya is 1 millisecond. So, we have to finalize this. 13 plus 1 is equal to 14 milliseconds. At 14 milliseconds, process P5 is finished. Okay, so this is now in consideration of the arrival time, the implementation of round robin. Okay, let us check on our concept on time quantum and context switch. In this example, the process time is equal to 10. Okay, so if the process time is equal to 10 and you are given of 12 quantum, you have 0 context switches. Why? Because this process time, this burst time will be finished in 1 context switch. Actually, may sobra ka pang 2 time quantum in this case. So, we have, in this case, process time is equal to 10 and the quantum time slice is equal to 12. Our context switch is equal to 0. So, in this example, if our burst time or the process time is 10 and you are given of a time slice of 6, you have 1 context switch. Yung unang cut po is 6 milliseconds. May natitira sa next cycle na 4 milliseconds. So, then, you have to preempt once and the context switch is equal to 1. In this given here, we have 0 to 10. 0 to 10. Yung burst time niya is also 10 milliseconds, but you are given of a time slice which is equal to 1. So, in this case, there are preemption. How many times yung preemption? So, unang preemption is here. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So, there are 9 context switches in this example. A multi-level queue scheduling algorithm partitions the ready queue into several separate queues. So the processes are permanently assigned to one queue, generally based on some property of the process such as yung sabi natin kanina na memory size, yung process priority, or the process type. Each queue has its own scheduling algorithm. So for example, separate queues might be used for foreground and background processes. So we have the foreground queue that might be scheduled by a round robin scheduling algorithm. Tapos yung nasa likod naman halimbawa is the FCFS. So in addition, there must be scheduling among the queues which has commonly implemented as a fixed priority preemptive scheduling. So for example, the foreground queue may have absolute priority over the background queue. So let's look this example. Halimbawa, let's look at this example of a multi-level queue scheduling algorithm with 5 queues listed in order of priority. So we have the systems processes as the highest priority. Comes after is the interactive processes, interactive editing processes, the batch processes, and the least priority in this example is the student processes. Okay, yung first concept po, it was multi-level queue. Ito naman yung pag-uusapan po natin is multi-level feedback queue. So when the multi-level queue scheduling algorithm is used, processes are permanently assigned to a queue. So when they enter the system, it is considered as permanent. If there are separate queues for foreground and background processes, processes do not move from one queue to the other since processes do not change their foreground or background nature. So this multi-level feedback queue has the advantage of low scheduling overhead. So the multi-level feedback queue scheduling algorithm, in contrast to the previous discussion of multi-level queue, allows a process to move between queues. The idea is to separate processes according to the characteristics of their CPU burst. If a process uses too much CPU time, it will be moved to a lower priority queue. So this scheme leaves the input-output bound and interactive processes in their higher priority queues. In addition, a process that waits too long in a lower priority queue may be moved to a higher priority queue. So this form of aging prevents starvation. In general, a multi-level feedback queue scheduler is defined by the following parameters. We have the number of queues, the scheduling algorithm for each queue, the method used to determine when to upgrade the process, method used to determine when to demote a process, and method used to determine which queue a process will enter when that process needs service. Okay, so let us now illustrate the multi-level feedback queue example. We have Q0, which is for round robin with time quantum 8 milliseconds. Then the next queue would be still RR, and the time quantum this time is 16 milliseconds. Then comes after is our Q2 for the first come first serve. So how it will appear if we have this kind of scheduling. So in this example, so in this example, we have the multi-level queue. Multi-level queue on a variation of multi-level feedback queue. So a process in Q0, in Q0 is given a time quantum of 8 milliseconds. So if it does not finish within this time, it is moved to the tail of the Q1. So if Q0 is empty, the process at the head of the Q1 is given a quantum of 16 milliseconds. It is preempted and is put into Q2. Processes in Q2 are run on an FCFS basis but are run only when queues 0 and 1 are empty. One distinction between user level and kernel level threads lies in how they are scheduled. So on systems implementing the many-to-one and many-to-many models, the thread library schedules user level threads to run on an available lightweight process. So this scheme is known as the process contention scope. since competition for the CPU takes place among threads belonging to the same process. So when we say the thread library schedules user threads onto available lightweight processes, we do not mean that the threads are actually running on a CPU. That would require the operating system to schedule the kernel thread onto a physical CPU. So to decide which kernel level thread to schedule onto a CPU, the kernel uses System Contention Scope, or the SCS, computation for the central processing unit with system contention scope takes place among all thread in the system. So systems using the one-to-one model such as Windows, Linux, and Solaris schedule threads using only the SCS, or the system contention scope. Next. Okay. We have here the pthread scheduling. So the POSIX thread API that allows specifying PCS or SCS during thread creation, we have identified the following contention scope values. So the pthread scope process schedules threads using process contention scope scheduling. The pthread scope system schedules using system contention scope scheduling. Okay. Next, we have here the implementation. In this figure, we illustrate a pthread scheduling API. The program first determines the existing contention scope and sets it to pthread scope systems. So it then creates 5 separate threads that will run using the SCS scheduling policy. Note that on some systems, only certain contention scope values are allowed. Example, si Linux and Mac OS systems allow only pthread scope system. Okay, if I may update, we have discussed concepts on CPU scheduling algorithm, and then we have a while ago discussed the thread scheduling algorithm. This time, we'll have the integration of multiple processor scheduling. Our discussion so far has focused on the problems of scheduling the CPU in a system with a single processor. So if multiple CPUs are available, there is now load sharing. It becomes possible, but scheduling problems become correspondingly more complex. Many possibilities have been tried, like as we saw with the single processor, the CPU scheduling. There is no one best solution, even though there are variations a while ago. We discussed several concerns in a multiprocessor scheduling. We concentrate on systems in which the processes are identical. So if it is identical, we say it's homogeneous. So in terms of their functionality, they have common implementation. We can use any available processor to run any process in the queue. However, that even with homogeneous multiprocessors, there are sometimes limitations on scheduling. Consider halimbawa a system with an input-output device attached to a private bus of one processor. Processes that wish to use that device must be scheduled to run on that processor. One approach to CPU scheduling in a multiprocessor system has all scheduling decisions, input-output processing, and other system activities handled by single processor, or we call it as the master server. The other processors execute only user code. So this is asymmetric processing, which is simple because only one processor accesses the system data structures. Thus, it reduces the need for data sharing. A second approach is symmetric processing, or the SMP, where each processor is self-scheduling. All processes may be in a common ready queue, or each processor may have its own private queue of ready queue processes. Regardless, scheduling proceeds by having the scheduler for each processor. We examine the ready queue and select a process to execute. multiple processors trying to access and update a common data structure, so the scheduler must be programmed carefully. We must ensure that two separate processors do not choose to schedule the same process and that processes are not lost from the queue. So virtually all modern operating systems support SMP, including Windows, Linux, and Mac OS. So consider what happens to cache memory when process has been running on a specific processor. The data most recently accessed by the process populate the cache for the processor, and as a result, successive memory accesses by the process are often satisfied in the cache memory. Consider also what happens if the process migrates to another processor. The contents of cache memory must be invalidated for the first processor, and the cache for the second processor must be repopulated. Because of the high cost of invalidating and repopulating the cache, most SPMP systems try to avoid migration of processes from one processor to another, and instead, it attempts to keep a process running on the same processor. This is known as processor affinity. That is, process has an affinity for the processor on which it is currently running. Processor affinity takes several forms. So when operating system has a policy of attempting to keep a process running on the same processor, so it guarantees it does not guarantee that it will always do so. There is a situation known as soft affinity. So the operating system will attempt to keep a process on a single processor, but it is possible for a process to migrate between processors. In contrast, some systems provide system calls that support hard affinity, thereby allowing a process to specify a subset of processors in which it may run. Many systems provide both soft and hard affinity. The main memory architecture of a system can affect processor affinity issues. So this figure illustrates an architecture featuring non-uniform memory access, or NUMA, in which a CPU has faster access to some parts of the main memory than the other parts. So in this case, this is the main memory of this processor. So it is faster if it has to access its own memory compared to other memory which is located on some other parts. So this occurs in systems containing combined CPU and memory boards. The CPUs on a board can access the memory on that board faster than it can access the memory on the other boards. If the operating system's CPU scheduler and memory replacement algorithms work together, then a process that is assigned affinity to a particular CPU can be allocated memory on the board where that CPU resides. SMP, or symmetric multiprocessing systems, have allowed several threads to run concurrently by providing multiple physical processors. However, a recent practice in computer hardware has to place multiple processor cores on the same physical chip, resulting in a multi-core processor. Each core maintains its architectural state and thus appears to the operating system to be a separate physical processor. Symmetric multiprocessing systems that use multi-core processors are faster and consume less power than systems in which each processor has its own physical chip. Multi-core processors may complicate schedule issues. Consider halimbawa the view of the researchers. Researchers have discovered that when a processor accesses a memory, it spends a significant amount of time waiting for the data to become available. So this situation is known as a memory stall. It may occur for various reasons like cache miss, that is accessing data that are not in cache memory. We turn next to a description of a scheduling policy. like scheduling policy of Linux, Windows, and Solaris operating systems. Well, it is important to note that we use the term process scheduling in a general sense here. In fact, we are describing the scheduling of the kernel threads with Solaris and Windows systems and tasks within the Linux scheduler. This table shows the dispatch table for scheduling, time sharing, and interactive threads. So these two scheduling classes include 60 priority, so that is 0 to 59. The dispatch table shown contains the following fields. You have the priority, the time quantum expired, and return from sleep. So isa-isahin po natin. First is the priority. The class-dependent priority for time sharing and interactive classes. A higher number indicates a higher priority. So as an example, in Solaris, the dispatch latency table is indexed by the priority level of the thread. To understand an entry, let's use priority 30 as an example. At priority 30, the thread has 80 milliseconds to complete its work, or it will be forced off the CPU. In the event that it does not complete its work, the system will context switch the thread off the CPU and change its priority. So if the case priority is now 20, at priority 20, our time quantum is now 120 milliseconds. So lowered priority to keep the thread from hogging the CPU, and that it can increase in the time quantum. It hopes that when we do not get back on the CPU, we have more time to complete our work. Next is the time quantum. The time quantum for the associated priority. This illustrates the inverse relationship between priorities and time quanta. The lowest priority, that is priority 0, has the highest time quantum, that is 200 milliseconds, and the highest priority, which is priority 59, has the lowest quantum, which is in 20 milliseconds. Time quantum expired. Okay, this one. This is the new priority of a thread that has used its entire time quantum without blocking. Such threads are considered CPU intensive. As shown in this table, these threads have their lowered priority, so compared to other columns. Now, to consider the last column, we have the return from sleep. The priority of a thread that is returning from sleeping such as waiting for an input-output. So when an input-output is available for a waiting thread, its priority is boosted between 50 to 59, supporting the scheduling policy of providing good response time for interactive processes. Threads in the real-time class are given the highest priority. A real time, halimbawa, yung kailangan yung responses na mabilisan, which is in real time, it will run before a process on any other class. So this assignment allows a real-time process to have a guaranteed response from the system within a bounded period of time. Like when you type in on the keyboard and agad-agad there are responses from our output device. So it requires real time. In general, few processes belongs to the real-time class are considered. Solaris uses the system class to run kernel threads, such as the scheduler and paging daemon. Once the priority of a system thread is established, it does not change. The system class is reserved for kernel use, that is, user processes running in kernel mode are not in the system class. This figure illustrates scheduling classes. Classes relate to one another and how they map to global priorities. Notice the kernel maintains threads for servicing interrupts. These threads do not belong to any scheduling class and execute at the highest priority, which is 160 to 169. As mentioned, Solaris uses the many-to-many model but switched to one-to-one model beginning with Solaris 9. Windows has preemptive priority scheduling that gives a real-time response on the higher priority processes compared to normal processes. There are 32 level of priorities. Ito, that is 0 to 31. There are 32 levels of priority, each with its own unique queue. The operating system changes priorities of normal processes to help improve response times and mitigate servation problems. Windows also supports load balancing by attempting to make evenly distributed initial assignments of threads to processors. The Linux operating system started out using a traditional Unix scheduler, but in more current revisions, began using something called Completely Fair Scheduler or the CFS. The standard Linux has two scheduling classes, default and real time. Each class has its own priority and scheduling algorithm. The Completely Fair Scheduler is the algorithm used for the default class. CFS assigns a proportion of CPU time to each task. Accordingly, we have the nice value, which is a quantity traditionally used in Unix-like systems as a component of the process priority formula. This figure describes modern Linux operating system. It provides improved support for SMP or symmetric multiprocessing systems and a scheduling algorithm that runs in time. So as the number of processes increases, the relative priority decreases. So its relative priority decreases. The Linux scheduler is a preemptive priority-based algorithm with two priority ranges. That is real-time, that is from 0 to 99. And we have the nice or other task range from 100 to 140. Unlike Solaris or XP, Linux assigns longer time quantums to higher priority tasks. Next, we have the runnable task. A runnable task is a task considered eligible for execution as long as it has not consumed all the time available in its time slice. Those tasks are stored in an active array. So tasks are stored in an active array. When a process consumes its time slice, it is moved to an expired array. The task priority may be reassigned as a part of the transferal. When the active array becomes empty, when the active array becomes empty, the two arrays are swapped. So these arrays are stored in run queue structures. On multiprocessor machines, each processor has its own scheduler with its own run queue. How do we select a CPU scheduling algorithm for a particular system? Well, there are many scheduling algorithms, each with its own parameters. As a result, selecting an algorithm can be difficult. The first problem is defining the criteria to be used in selecting an algorithm. Criteria are often defined in terms of CPU utilization, the response time, or the throughput. To select an algorithm, we must first define the relative importance of these elements. So our criteria may, however, include the measures that we have studied previously, and those are how we maximize CPU utilization under the constraint that maximum response time is 1 second, maximizing the throughput such that the turnaround time is on average or linearly proportional to the total execution time. Once the selection criteria have been defined, we want to evaluate the algorithms under consideration. So we next describe the various evaluation methods. So in this case, we'll be describing the queuing models, the implementation, simulation, and deterministic modeling. One major class of evaluation method is analytic evaluation. Analytic evaluation uses the given algorithm and the system workload to produce a formula or number to evaluate the performance of the algorithm for that workload. Deterministic modeling is one of the type of analytic evaluation. This method takes a particular predetermined workload and defines the performance of each algorithm for that workload. For example, we assume that we have the workload. All 5 processes arrive at time 0. So in a given order with the length of the CPU burst, we have this in milliseconds. Okay, so the algorithm that would give the minimum average time would be considered. So in this implementation, we'll be considering later the SJF and the round robin, and on which we have the unit for time, which is in milliseconds. The time is 0 milliseconds for process P1. So no waiting time for process P1. Then we have 10 milliseconds for process P2, 39 milliseconds for process P3, 42 milliseconds for process P4, and 49 milliseconds for process P5. Thus, the average waiting time is 0 plus 10 plus 39 plus 42 plus 49 divided by the number of processes, which is equal to 5. So in this case, we have 28 milliseconds for deterministic modeling. With non-preemptive SJF scheduling, we execute the process. And as the waiting time is 10 milliseconds for process P1, we have 10 for process P1, and then we have 32 milliseconds for process P2, 0 milliseconds for process P3, 3 milliseconds for process P4, and 20 milliseconds for process P5. So if we are to compute the average waiting time, we have 10 plus 32 plus 0 plus 3 plus 20 divided by 5. So this results to 13 milliseconds. With the round robin implementation, the summary of the waiting time is 0 milliseconds for process P1, 52 milliseconds for process P2, 20 milliseconds for process P3, 23 milliseconds for process P4, and 50 milliseconds for process P5. Thus, the average waiting time is 0 plus 52 plus 20 plus 23 plus 40 divided by 5. So it is equal to 27 milliseconds. So we can see that in this case, the average waiting time obtained with the SJF policy is less than half that obtained with the first come first serve kanina. Round robin scheduling gives us an intermediate value. So deterministic modeling is simple and fast. It gives us exact numbers, allowing us to compare the algorithms. However, it requires exact numbers for input, and its answers apply only to those cases. So the main uses of deterministic modeling are in describing scheduling algorithms and providing examples. So in cases where we are running the same program over and over again and can measure the program's processing requirements exactly, we may be able to use deterministic modeling to select a scheduling algorithm. Further, over a set of examples, deterministic modeling may indicate trends that can be analyzed and proved separately. For example, it can be shown that the environment described which all processes and their times available at time 0. So in this case, the SJF policy will always result in the minimum waiting time. Most of our implementation is on deterministic modeling, but we will also try to discuss queuing models, as this is also related to the evaluation of the algorithm. On many systems, the processes that are run vary from day to day, so there is no static set of processes or times to use for deterministic modeling. What can be determined, however, is the distribution of the CPU and input-output bursts. These distributions can be measured and then approximated or estimated. The result is a mathematical formula describing the probability of a particular CPU burst. Commonly, this distribution is exponential and is described by its mean. We can describe the distribution of times when processor arrive in the system. So this is the arrival time distribution. From these two distributions, it is possible to compute the average throughput, the utilization, the waiting time, and many other factors on CPU scheduling algorithm. The computer system is described as a network of servers. Each server has a queue of waiting processes. The CPU is a server with its ready queue. So there is also input-output system with its device queues. Knowing the arrival rates and the service rates, we can compute the utilization, the average queue length, the average waiting time, and all the factors described here are for queuing network analysis. As an example, let N be the average queue length excluding the processes that is being serviced. Let W be the average waiting time in queue, and let the W be the new process that will arrive in the queue. If the system is in a steady state, then the number of processes leaving the queue must be equal to the number of processes that arrive. Thus, N is equal to times W. So this equation is known as Little's formulas, and this is particularly useful because it is valid for any scheduling algorithm and arrival distribution. We can use Little's formula to compute one of three variables if we know the other two. So for example, if we know that 7 processes arrive every second on an average, and that there are normally 14 processes in the queue, then we can compute for the average waiting time per process as 2 seconds. So queuing analysis can be useful in comparing scheduling algorithms, but also it has its limitations. At the moment, the classes of algorithms and distributions that can be handled are fairly limited. The mathematics of complicated algorithms and distributions can be difficult to work with. Thus, arrival and service distributions are often defined in mathematical track table. So, however, it is, as I said, unrealistic ways. So, it is also generally necessary to make a number of independent assumptions, which is also may not be accurate. As a result, these difficulties, queuing models are often only good for approximations of real systems, and the accuracy of the computed results may be in question. Next is the simulation model. Even a simulation is of limited accuracy, the only completely accurate way to evaluate a scheduling algorithm is to code it up. Put it in the operating system and see how it works. This approach puts the actual algorithm in a real system for evaluation under real operating conditions. So the major difficulty with this approach is the high cost. The expense is incurred not only in the coding of the algorithm and modifying the operating system to support it, but also in the reaction of the users to constantly changing operating system. Most users are not interested in building a better operating system. They want to get their processes executed and use their results. Yun na yung gusto nila. So, a constantly changing operating system does not help the users to get their work done. Another difficulty is that the environment in which algorithms is used will change. So the environment will change not only in the usual way, however, there are new approaches that may reveal. Running simulation involves programming a model of the computer system. Software data structures represent the major components of the system. The simulator has a variable representing a clock. As the variable's value is increased, the simulation modifies the system state to reflect the activities of the devices, the processes, and the scheduler. As the simulation executes, statistics that indicate algorithm performance are gathered and printed. The data to drive the simulation can be generated in several ways. So the most common method uses a random number generator that is programmed to generate processes. CPU burst times also are considered, the arrivals, departures, and many other factors. So according to probability distributions, the distributions can be defined if it's uniform or decay exponential. If a distribution is to be defined in terms of measurements, then the actual system under study are taken. The results define the distribution of events in the real system. This distribution can be used to drive the simulation. A distribution-driven simulation may be inaccurate. However, because of relationships between the successive events in the real system, it is deemed ideal. The frequency distribution indicates only how many instances of each event occur. It does not indicate anything about the order of their occurrences. So to correct problems, we can use the trace tapes. So we create a trace tape by monitoring the real system and recording the sequence of actual event. So when I then use the sequence to drive the simulation. Trace tapes provide an excellent way to compare two algorithms on exactly same set of real inputs. So this method can produce accurate results for its inputs. The simulations, however, can be expensive, often requiring hours of computer time. A more detailed simulation provides more accurate results, but it also takes more computer time. In addition, trace tapes can require large amount of storage space, so the design, the coding, and debugging of the simulators can be a major task. An alternative strategy to SPMP is SMT. SMT stands for Symmetric Multi-Threading, in which multiple virtual CPUs are used instead of multiple physical CPUs. SMT must be supported in hardware as each logical CPU has its own registers and handles its own interrupts. To some extent, the operating system does not need to know if the processors it is managing are real or virtual. On the other hand, some scheduling decisions can be optimized if the scheduler knows the mapping of virtual processors to real CPUs. The amount of time required for this scheduling dispatcher to stop one process and start another is known as dispatch latency. Providing real-time tasks with immediate access to the CPU mandates that real-time operating systems minimize this latency. The most effective technique for keeping dispatch latency low is to provide preemptive kernels. So in this figure, we diagram that makeup of dispatch latency. So there is a conflict phase of dispatch latency, and that is categorized into the two components: preemption of any process running in the kernel, the release by the low priority processes of the resources needed by a high priority process. So as an example, in Solaris, the dispatch latency with preemption disabled is over 100 milliseconds. With the preemption enabled, it is reduced to less than a millisecond. The Java runtime environment supports a very simple deterministic scheduling algorithm called fixed priority scheduling. So this algorithm schedules threads on the basis of their priority relative to other runnable threads. So when a thread is created, it inherits its priority from the thread that created it. A higher priority thread becomes runnable. First in, first out queue is used if there are multiple threads with the same priority. The Java thread scheduling features the JVM schedules using a preemptive priority-based scheduling algorithm. All Java threads have a priority, and the thread with the highest priority is scheduled to run by the Java machine. So in case two threads have the same priority, a first in, first out ordering is followed. So different thread is invoked to run in case one of the following events occurs, like the currently running thread exits the runnable state, and that is either it blocks or it terminates. A thread with higher priority than the thread currently running enters the runnable state. The lower priority thread is preempted, and the higher priority thread is scheduled to run. Some systems limit selfish thread behavior with a strategy known as time slicing. Time slicing comes into play when multiple runnable threads of equal priority are the highest priority threads competing for the central processing unit. A thread can voluntarily yield control through the yield method. So whenever a thread yields control of the central processing unit, another thread of the same priority is scheduled to run. So a thread voluntarily yielding control of the CPU is called cooperative multitasking. JVM selects to run a runnable thread with the highest priority. All Java threads have a priority in the range 1 to 10. Top priority is 10, lowest priority is 1. Whenever a Java thread is created, it has the same priority as the thread which created it. Thread priority can be changed by the set priority method. Interactive class uses the same scheduling policy as the time-sharing class, but it gives windowing applications to higher priority for better performance. It uses the system class to run kernel processes such as the scheduler, the paging daemon, and the like. The priority of a system process, once established, never changes. User processes running in system mode do not belong to the system class. The scheduling policy for the system class does not time slice, like a process belonging to the system class runs until it blocks or is preempted by a higher priority process. Processes in real-time class are given the highest priority. So each scheduling class includes set of priorities. The scheduler converts the class-specific priorities into global priority and selects the process with the highest global priority. Okay. Well, that's it for chapter 5. This is now for the topic CPU scheduling. So please be ready for our next evaluation next meeting.